First of all, I would want to thank Professor Stark to invite me here to give a lecture that I have already given in Osaka in December, actually. And so some of the audience might have already known what I have said, but this time I think I will organize some of the content and add a little bit more into the lecture. So let me start. The title of my lecture is So mainly, I'm interested in locally standard Z2-torus sections. Z2-torus means Z2, Z2, and Z2n. So let me first introduce some background. And in 1991, Davis theory introduced a collection of manifolds called small cover. Basically, the small cover is an effective action of Z2n on an m-dimensional closed manifold, such that it is locally standard. And this means that each point of M has a Z2n invariant neighborhood, which is an equivariant homomorphic to the standard action of Z2n on Rn. I mean, the standard action of Z2n on Rn is just a reflections. I mean, the generators of this Z2n act by reflections about the hyperplanes in Rn. So this is called a standard Z2n action on Rn. So locally standard means that each point of M has an Z2n invariant neighborhood that is equivariantly homomorphic to invariant open neighborhoods in this model. So actually, the concept of local standard actually includes a free action. So we will see, but small cover is not free. I mean, this action is not free. But actually, the concept itself includes free action. And another condition is for small cover, the object space is a simple convex polytope. And because of this property, many of the topological information of M can be read directly from the combinatorics of the simple polytopes. And also, they write down a gluing rule. The gluing construction for small cover is like this. So suppose we have a simple polytope. So this is a polytope. And we cross it with Z2n. So we take 2 to the n copies of Pn, and then we glue some points. We glue Pg and P prime G prime if P equals P prime and the G prime minus G is in this group. I mean, this Fp is a phase of P that contain P in the interior, in the relative interior. So each point on this polytope is contained in some phase that contain P in its relative interior. and GFP is a
I have a stupid question. What P is F of P? Large P or small P?
This.
Yes, yes. This
P is
P.
a small P, right?
This is small.
You are using two P's.
Oh yeah, yeah.
So this is stupid question.
Yeah, this is small p and small p and p prime is a
That
point.
is small P, P, right?
And it contain, yeah, this is small p.
This is small P.
A small p, yeah. So Fp is a phase of a big P that contains a small p in the relative interior. And this group is decided by this action. Basically, this group is the isotropic group of the point of this phase under this action, because this action has some fixed points. So we can write down G Fi1 Fik is, well, is lambda I1 lambda Fik in Z2n, where lambda Fi is the isotropy. Fi. So for any facet, we can write any phase as the intersection of some facets. So the isotropic group of this small phase.
Projective inverse.
Yes.
Of the
Because polytope does not have any action. Actually, isotropic
Oh, yeah, okay,
pi
okay.
inverse.
Isotropic group of this pi inverse. Yeah, because on the polytope, of course, there's no action. Okay. Another source of example comes from Zilu and
Actually, pi inverse of interior. Interior.
oh yeah, right. The pi inverse of the interior of that line. Another source of example comes from Zilu and Professor Ikemasta's work. They define some sort of generalized locally standard action. The difference between their example and this is they do not require this. It is arbitrary. It's arbitrary. It would be a nice manifold with corners. So here we require the object space simple polytope, but they started the case when the object space it could be a very complicated, nice manifold with corners, i.e. this may not be contractible, so it may contain some holes in it. And then to decide, and if we want to see what kind of information are needed to completely decide this action, we found that decide. This action decide two data. Well, the first one is actually a Z2m bundle, a principal bundle over the interior of the end. This is the quotient space. Okay. So again, I denote the object space at the end. But now Vn may not be a polytope. It could be nice manifold with corners. So because this may have some non-trivial homology itself, so the free orbits, and this actually has some free orbits which correspond to the interior of this manifold. And then this action will decide a principal Z2M bundle over this. And this bundle may not be trivial. But in a small curve case, that's always trivial because it's a polytope. So the interior polytope is contractible. That's why the bundle is trivial. But this one may not be trivial.
The Z2N is not the principal Z2.
Oh, right. Yes, it's Z2N bundle. And also we have Z2N coloring lambda on the boundary of this. So this is basically like this. So this encodes the isotropic group of the facets, interior of the facets, on the boundary of this orbit space. And their theorem says actually we can recover this action up to equivariant homomorphism by this bundle. So I denoted by Xi, and by lambda. Okay, so
Is this a principal bundle?
yeah. Xi is a principal bundle over actually the interior, over actually the interior of the BN.
Not it's just over this manifold.
Oh, the action is
Yeah.
No,
interior.
Yeah.
So cutting out some.
Yeah, there's something. Yeah.
Yeah, I think strictly speaking, the Xi is a principal Z2M bundle over the interior because the interior is the free orbits.
Yeah, but now we just consider the Z2N bundle, principal bundle over the total orbit space, and not the interior.
Yeah, but I think the treatment. I think in my treatment, I think it's more natural to consider is this.
You can look at the neighborhood, like of the boundary.
Yeah.
Yeah.
Also, you can take smaller neighborhood.
Yeah.
And then take its closure, and it will be like the whole thing, but the action will be free, right? You just take epsilon from the boundary,
Yeah.
and then you get something open,
Right,
and then
right,
you close it.
Yeah,
and
yeah.
you get something homomorphic to the whole thing, but over these actions, it's free.
Yeah.
so you sort of desingularifying, or how they call it, resolution of singularity at the fixed point,
Yeah.
or the non-singular.
Okay. So we can recover. So we can recover that. So this action from Xi and lambda. So these are the essential information that decided this locally standard action. So and in the talk today, I want to somehow generalize the meaning of locally standard. So I have to slightly generalize the meaning of locally standard. Well, in the above two sources of examples, the rank of the torus equals the rank of the dimension of the manifold. But now I want to make sense of this. A locally standard action on Z2M on Mn. I mean, the rank M may not be n. So from the definition, so we should first make sense of what does it mean of standard. I mean standard Z2M action on Rn. Okay. So we should first make sense of this, and then we should say, well, what does it mean locally standard? Okay. So how to define it? So I think that there's a very natural choice. when m is less or equal to n, so I can say for any g1, gm in Z2m, this action is very, I think it's a very natural choice for our definition of standard. Okay, this one. So I just let the first n coordinate of this group act like the reflection, and then the other just fixed. And the object space of this one is actually not it's not a cone, but just it's like R N M, so equals n with x I greater or equal to 0 and I. Okay, so this case when m is less or equal to n. Okay, probably like this.
This is the object domain.
Yeah, this is obviously of this standard action on Euclidean space. But when m is greater than n, so we should make sense of what does mean. So it seems there's no very good choice like definition like this. But still we can somehow say Z2m. So I think one Rn is not enough. So we should let it act on Rn cross Z2m minus n, and then something like x1. So we take because we want the action to be effective. So I think this one cannot be enough. So we take 2 to the n minus n copies of Rn, and then I write something like C1. So the first coordinates is the coordinate of Rn, and then n minus n. Okay. So for any element like G1, Gm here, I G1 Gn times n, and then C1 plus H1 plus G m plus 1 H m minus n plus G Tm. Okay. So basically this action means that this group will act by reflection in Rn, and then the other components, I mean the last n minus n components of this group will act by permutating these copies of this Rn. So that's the meaning of so the last n minus n elements will just permutate these 2 to them copies of Rn, and the first n components will just as before, just the reflection of the Rn. Okay. So I consider things here as standard because they look very natural, and then they some of the local properties are very similar to the locally standard action by Davis and by Jilu and Professor Masta. Okay, and then
here the object space for this case the object space would be
and right. The object space now is a cone now. Something like this. The object space will be the positive cone. Okay.
So that H, where it belongs?
H is Z2. Yeah.
So in M is greater than N,
yeah.
you are just multiplying the space.
Yeah.
Several copies of it.
Yeah, right. Yeah, or else the action is not effective. Yeah. So there must be some 2 to the n minus n copies, and then to make this action effective. So this seems to be me very natural. I mean, although.
And when you write this R plus n comma m, there is no m in the right hand side. That's why they can see so.
R.
No. Yeah, just 2 lines higher, right? R. Yeah, this one. So here you have m in the left hand side of that.
Yeah, this is when
I should be less than between M. Xi is greater than 0 when I is from between 1 and N.
Yes,
M appears there.
M is less than.
Yeah, but x's are 1 through xm, right?
Right, but only the first M coordinate should
But
be
that's N.
positive.
Yeah, I understand, but that's n or m. That x1 through x
M.
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 x1 xm.
M.
Oh, everything is rm, right? Yes.
Yeah, because I only do reflection in the first M coordinates. Oh. So the problem
It's like the trivial.
Yeah, okay, and then I can still make sense of make sense of the meaning of locally standard action. So Z2M action on a manifold. So I say locally every point has an invariant Z2M neighborhood that is locally standard to invariant open sets in this standard model. Okay, so that's the meaning of my locally standard Z2M action on the n-dimensional manifold, no matter what M is. Okay, and then the properties. The object space I denoted by xn is still a nice manifold with corners. Here I have to emphasize the meaning of nice, because sometimes you may be confused, because this may not have vertices really. I mean, we can say manifold with edges or something. So nice means that so this is a manifold with corner, and any codimension k face is the intersection of k facets.
But globally, not locally.
Globally. Any codimension k face is the intersection of k different facets. So I can draw some examples of nice manifold with corners. So like this. This is square. So this is very canonical one. And then, but this one is not nice because this is only one face, and then this is a codimension two. I mean, this is a vertex, but it's the intersection of one face. So that's considered not nice. But here you see, suppose we have a disk with a round, the round disk. The boundary is just a circle. Okay. So actually, this one is considered nice. Actually, this one is considered nice. Yeah. Also, you can draw some picture like this. You can have say the side of the cylinder is so we have a solid cylinder, and the side of the cylinder is a face, top and bottom is a two face, and this is also nice. Although their intersection is not it's not contractible. Okay. And on the object space, we can.
But the facets are connected, right?
The facets. In my discussion, I think the object I consider the object space is connected. I mean, I also assume.
But I mean, what is a facet then?
Should be connected. but
Yeah,
the
yeah.
intersection
Yeah,
may
yeah.
not
Yeah,
connect.
intersection.
Yeah, their intersection may not be connected, but I consider facets as a connected n-1 dimensional submanifold on the boundary. Okay, and then still, and similarly, you have this this coloring, a Z2M coloring. On Xn. So for any facet Fj, so a coloring mu Fj is defined to be the element of Z2M that fixing pi inverse of Fj pointwise. So this is a coloring. So this is the same as the characteristic function of small cover or the coloring before. And also we have a principal bundle. Principal bundle over the interior of this orbit space, because the interior corresponds to 3 orbits. And similarly, I can show that any such action actually is completely decided by mu, by the orbit space mu, and it's the principal bundle. So the arguments are fairly similar to the arguments given by Professor Liu and Professor Masta. So let us see some very interesting example. So suppose we have a pentagon, and then suppose Z2-3 locally standard in the sense here, locally standard Z2-3 action on the connect sum of torus, and then the orbit space could look like this. E2, E3, E2, and then E1, E2, E3. So this is a basis of E2. And so this is one of the example of locally standard E2-3 action on this surface. Although this picture looks weird, but because it's different from the small cover. But anyway, we can apply the same gluing rule to this one as small cover, and then recover this manifold. Yeah, I think this is the main motive for me to understand, to define all this conception, because I want to understand the meaning of this thing, because it's not obvious what it is just by looking at this. Right? It's not very obvious by gluing the 8 copies of pentagon, and then what do we get? Actually, we get this. Later, I just ask myself, so when when X is not contractible, then the principal bundle actually could be non-trivial. And then in this case, how does the gluing rule apply to give back? I mean, see, and how this information give back to our action. Right. So this is a problem. Well, there is a very formal way to do that actually, but I'm not quite satisfied with the way given before. So I really like the idea of say taking some copies of this and divided by some relation, and some formal definition like gluing different blocks of space and then identify their boundary and get the manifold. But actually, I cannot directly use this one when X is not contractible. Because the information, I mean, the principal bundle cannot be directly interpreted as some sort of coloring on the facets of the underlying space. So what I did here is to interpret the principal bundle as some sort of coloring on a manifold with corners. But that manifold with corners is not Xn itself. It's just so I will explain the meaning of that manifold. It's not easy to be interpreted as coloring. Yeah, because this is a coloring on the boundary facets of Xn, but this one is not. It's just some boundary over the interior of Xn. So the tastes are quite different from the coloring. So I really like the idea of coloring. Okay, and I want to define some manifold that can encode the information of both of these. But how to do that? Okay, so first, so let's assume Xn is a closed manifold. Because in our definition, actually, when Xn has no boundary, I mean it's a closed manifold, then this action is totally free. I mean it is just a regular Z2m covering space over Xn. So we can consider so we can consider this case first, and then suppose we have a principal. So this is a principal bundle over a closed manifold. So how to understand? Say this is C. So how to use some sort of gluing way to recover M? So of course in the textbook we know how to construct covering space. We use the homotopy class of paths, right, to recover any manifold. But I think for our purpose, it is not that necessary, because in general, when the fundamental group of the QN is not abelian, when the fiber is not a abelian group, then it could be very complicated. But for our purpose, because this one is a abelian group, so we can somehow simplify it. So recall that principal Z2m bundles over Qn can be identified with this. Right. So we identified with elements like this. So this is a classical map for the principal bundles. So suppose this is pi, and so we have this principal Z2m bundle gives an element. I denoted by gamma pi is lambda pi in H1 Q and Z2m. And by punctual duality we can think of it as this. This is by punctual duality. Okay, and in algebraic topology we know that, in differential topology we know that an element here actually can be represented by smooth embedding submanifolds of Qn. So suppose this is the basis. I should write it like this: a basis of Hn minus 1 Qn Z2. so each of them is embedding submanifold in Qn. So this bundle actually is a deciding element which assign a value to each of this embedding submanifold. Okay, so this information actually completely decided the principal bundle. So we obtain a map lambda pi from this basis to Z2m, which assign a value to gamma pi. Sigma I. Okay. So I use small lambda to represent this map. This is called associated Z2m coloring of pi. Okay. So the information is encoded by assigning a coloring to a basis of the n-1 homology groups of Qn. Okay, for example, when Qn is a torus, so any principal bundle over the torus is defined by some sort of coloring on its basis. I mean now a basis of torus, the first homology of the torus is these two circles. Okay, so for any Z2m coloring over the torus is given is defined by a coloring. Okay, lambda. But now Q is still closed. But how do we but how do we use the gluing idea to define such a bundle? Okay. So next we cut Qn open along sigma 1 to sigma k. So this is. So in this example, if I cut it open, I get a square. Okay. And then we have a nice manifold with corners automatically, because I can assume these embedding submanifolds intersect transversely in Qn. So if we cut it along these submanifolds, we will automatically get a nice manifold with corners. And then, so using this, I claim that I can use this idea to define a very formal gluing rule to recover this principal bundle. So what's the meaning of cut it open? So this means that choose a small neighborhood. It's a normal neighborhood. Neighborhood of sigma I in Qn. So I write it as n sigma I. So this is you can think of it as a line bundle over sigma I, and then remove the interior of this from Qn. Okay. So in this picture, it's like we remove a very thin neighborhood of these two circles, and then we get a square. The manifold I represented by Vn. Oh, okay. But do not. mix this symbol with the symbol I used before. So this Vn is, we cut a closed manifold open along a basis of the n-1 homology of the manifold. You will remove all these neighborhoods, and then we will get a this is a nice manifold with corners. And I give it a name, but I don't know if this is a very good name or not. I call it Z2-core. So this is a name invented by me. Well, from the construction, it is very easy to see that Z2-core is not unique. I mean, because we have many choices for the basis of this group. So of course this is far from unique, and sometimes it could be disconnected, and this one may not be connected, but I claim that there always exists a connected Z2-core. There always exists one. Always exists at least one. But you have to write some arguments for that. But it's not very hard. And in addition, the Z2-core may not be contractible. So this is quite surprising. Because it seems that it may not be contractible. Even if we cut it open, and it still may not be contractible. For example, so this is Q2, this is the surface, and then if we cut this open along a basis, okay, what we get is this.
If it is not orientable.
What?
If it is not orientable, it's okay.
Well, when it is not orientable, then we still I will show example when this is not orientable. So say for RP2, so if we cut open along or claim bottom. Okay. So this one we get something like this. We get disk. The basis of H1 of RP2 is a circle. And then if you cut along, and this is a Z2-core. But this one is something like this. So this is a little bit different from the torus. From these examples, you can see that Z2-cores of different manifold could be topologically the same, but the difference is the boundary map. I mean, and because it seems there are some extra structures on the boundary. Here you can see we identify this with this, and then we can recover the original manifold. So there are some extra structures on each of the Z2-core. The properties of Vn is this. The boundary of Vn is the boundary of the union of this neighborhood, and the Vn has a panel structure, i.e. its boundary consists of some facets, and the facets come from the same cut section of the manifold I denoted by Ki. So here this is P1, okay, because you come from one circle, and this P2. Okay. Well, of course here there's only one panel. And then there's an extra structure which encodes the cutting. Okay. Another thing is there's a tau I. There exists This is an involution. Involution on each of the panel, between the facets of the panel, such that tau I, pi kappa pj is in pi kappa pj, and satisfy certain commutative, the commuting relations. Well, you may wonder, what is tau I? Well, here you can see in each neighborhood, I mean, say, suppose this is sigma I, and this is n sigma I. The boundary of n sigma I is a double cover of sigma I. The boundary it's naturally a double cover. So the tau I could be, first I could just choose tau I to be the deck transformation of this double covering. So like this. So here is just identify the point to this here. But actually there's some subtlety here. You cannot directly choose this tau I as just a deck transformation of this double covering. Sometimes at their intersections, we must somehow deform it locally and then to make them commute. So this one, this condition is kind of technical, and you have to somehow deform it. The reason is that sometimes, say if you have intersection like this, right? So the set in this picture, I mean, their intersections. Actually, it's not invariant under tau I, and there's no commuting relations here. But somehow we can just deform it and so locally I think I can deform it to make it look like this picture. Okay, so I call this involutive panel structure. Well, panel structure is defined by many people before. I think basically by Borel or Davis, and in their papers you can find the meaning of panel structure. Here we have just some extra structure. In each panel we have some sort of involution, and then which commute at the intersections. So the Z2-core is really the thing that we can encode all the information of this principal bundle as some sort of coloring on it. So suppose, just now we have this coloring, sigma 1, sigma k. This is spaces to Z2m. And now suppose we have Z2-core and then P1, Pk, and I just number P1, number sigma 1, number sigma k. So assign the color to each of the corresponding panels. I mean, all the facets, say in Pi, is colored by lambda sigma. So in this picture, like, these two edges are colored by lambda sigma 1, and these two edges are colored by lambda sigma 2. Okay, so like this. So suppose it's this, and then okay, and then we can define a very formal glue back construction. So this is the thing I want to address. has some relations. The relation is xg is equivalent to x prime g prime if and only if x prime equals tau ix for some pi and g prime equals g plus lambda pi. Okay. So the rule is quite similar to the small cover. I think the only difference is in small cover, this is identity. But here I did not glue the 2 points with the same x. I glued this to somehow the involuted point, so you can think of it as some sort of dew point in a panel, and then the g coordinate satisfy this condition at the same time. So this construction is not very obvious from the original setting. So, in fact, here, many points actually glue to the same point. In fact, x prime g prime is equivalent to xg if and only if x prime is tau is tau I1 is 1 x g prime is g plus epsilon 1 lambda p1 I1 plus epsilon s lambda p is for any x in the intersection of s. Okay, right. So for any x is in the interior, so for any x in the interior of a codimension S faces, the point that is glued to xg is given by this form. So there are 2 to the s different points actually are glued to the same point here. Yeah, right here. For any x in the interior of a codimension S face, exactly 2 to the s different points here are glued together. So this is different from the small cover. Okay. And then I claim that this construction actually can recover our original principal bundle. But how to define the action? I mean here there's a very natural action to define on this space. This is x g plus g0. This space. For any x in the n g0 in Z2m. We can show that this action is free. I mean x g plus g0 is actually never. And this point is never equivalent to x g0. So actually this action is free action, free Z2m action. And we have a very easy argument to show that the orbit space of this action is a natural Z2m action on this space. The orbit space is actually Qn. Okay. And we have a very easy proposition. It shows that suppose this is a principal bundle. Then let lambda pi to be associated coloring of this bundle, and then we have for any Z2 core Vn is equivalent homomorphic to the Mn. For any, so this is a Z2 core. Z2 for any Z2 core of Qn. This will give back to our manifold Mn.
With this concept, you selected some manifold and white coordinate some manifold you select. Is this a dependent on some manifold?
Like this?
Yes.
Yeah, for any closed manifold, I think this is true. I mean, we can always find embedding some manifold.
Yeah, it's true. Is it depend on basis of
the Qn?
yes, your construction. If taking another basis and
Yeah, of course. Say if you give another so say if you take another one and then of course the Z2 core would be different. I mean, you can get another Z2 core and then you can apply the same rule and get back to Mn. So I mean this construction of course depends on how you choose this basis, this representative structure. But in many cases, we can choose some very easy ones. Okay, so let me give you some easy examples. Say suppose this is T2. Okay, Q2 to T2, and then so this is a Z2 core. It's a square. Okay, and then I colored by say this E1. So first of all, suppose it's 0. If the color is 0, I mean it's a torus. Suppose we color this by 0 and 0. So you can easily understand it as this is T2, 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 T2. Okay, this is the trivial bundle. Okay, and then if this is 0, 0, E1, E1, so you get T2, T2. Actually, it's 2 T2 because T2 itself is a double coloring of T2. Okay, so it's something like this. And suppose this is it is E1, E1, E2, and E2. Okay, then this will give you one torus. Because we have the double carbon in this direction and this direction. And there's one very interesting one. I mean, and this one, E1, 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 E1. Okay. They're all E1. This is not trivial. But it is something like, well, you can imagine, it must be 2-torus. It's still 2-torus. But the image of these two actually goes to something like a 1-1 curve. Okay, something like a 1-1 curve. So this is not like this. So they're quite different. Although they're all two components, but the image is quite different. This is a kind of twist. Do a twist. So this is a very easy example. And then another one is say the RP2. So like Q2 is RP2, and then its Z2 core is this. Okay. The involutive panel structure on the boundary is just identify the antipodal point of the circle. And then suppose this is 0, then of course this is Z2. Suppose I have a Z2-2. Suppose the coloring is in Z2-2. Okay, lambda is it. If lambda is 0, then it is 4 copies of RP2. 4 copies of RP2. RP2, RP2, and RP2. And so if this one is E1, then there are two spheres. Okay. And you can see that actually we can only mark it by one element. So this means that well this somehow implies that there's no free Z2-2 action on the. There could be no. Connected. So this is impossible. Okay. Okay. So these are the examples. So what time? I think I ran out of time so far. But I have not really finished. But I can first briefly tell you the idea in following. And now the interior. If the interior is not homologically trivial, then the bundle could be non-trivial. Then we can cut, and then we can still choose some manifold to cut this xn, and then to make it. So suppose I can choose sigma 1, sigma k, and then to cut it open, and then we will get something like manifold with corners un. And then remember here we already, for locally standard action, we have some sort of characteristic function on the boundary already. But if you cut it open, this principal boundary will give you a new sort of colorings in the panels that come from sigma I. So we have sort of two mixed type of colorings on the boundary of un. And then surprisingly, we can actually apply the same gluing rule. I remember how I defined the un plus Z2 they said xg is from g prime if x equals tau minus, then g prime is g plus lambda p. Okay, so this is a rule I used before, but I found that formally, actually I can use the same rule to recover the principal bundles over xn. Just formally, the rules are exactly the same. So I think probably this is a very nice way to think about the principal bundles over some locally standard action from the orbit space back. So this is like if we know the orbit space, and then we just assign some colorings on its boundaries and in the interior, and then we can somehow find a very formal way to recover the total space. The reason why I want to understand the problem in this way is I'm quite interested in another conjecture by Carson. Well, some people call it Halperin Carson conjecture. It says if for any free Z2M actions on MM, then the sum of the
free. You said
the free. Or you can understand the principle. Oh, sorry. A principle for any principal Z2M bundles over Qn, then or you can understand it some sort of free Z2M actions on a manifold. So these two viewpoints are equivalent. And then the HI of Mn Z2 I I think this is a this is a conjecture I'm really interested to know how to prove.
Definition. Definition.
Huh? What?
Yeah.
Yeah.
Definition.
Oh, the rank. It means the Z2-bit numbers of zero. Z2-bit numbers of Mn will add up. The sum of the Z2-bit number of Mn would be at least 2 to them. So the 0 dimension and the 1 dimension or 2 dimension cases are all very easy to verify. But the 3 dimension analysis, I think, is still open. Originally, this problem takes this form. So if Z2M acts freely on a product of spheres, in K, then M, less than K. So this is an old form, and probably 50 years ago, people begin to ask this question. Yeah, because this one is a special case of this one, because the sum of the Z2-bit numbers of this is 2 to the K. So I think right now I think I can use my construction to understand some of the special case when when Q is a certain type of manifold. I mean this conjecture is probably true. Of course, the GU and the student of Professor Torus and confirm some very special cases when this Z2-torus act on moment angle complexes or moment angle manifolds. Okay, I think I should just stop here.